right, the next presentation we have here in the sequence is going to be by Dr. Kevin Knuth. And this is Constraints on Societies Engaged in Relativistic Interstellar Travel. Dr. Knuth is a professor, an associate professor in the Department of Physics at University of Albany, SUNY, and is the editor-in-chief of the journal Entropy, MDPI. He is a former NASA research scientist, having worked for 4 years at the NASA Ames Research Center in Intelligent Systems Division, assigning artificial intelligence algorithms for astrophysical data analysis. He spent over 20 years of experience in applying Bayesian and maximum entropy methods to the design of machine learning algorithms for data analysis applied to the physical science. His current research interests include the foundations of physics, quantum information, inference and inquiry, autonomous robotics, and the search for and characterization of extrasolar planets. He's published over 90 publications, has been invited to give presentations in 14 countries. I've seen his presentation, it's fabulous. I'm excited about it, and I'm glad to have him here. Thank you. Hopefully this will be sufficient.
That sounds good. Yeah, that was fine. We can do that. Yeah, that should work.
And then here's your infamous clicker.
Give that a shot. I don't know if it's going to work.
Backwards. That's a
Okay,
waiter.
please.
Give it a shot and make sure it works.
All right, let's
I don't know if it will.
that works good. And laser, great. All right, well, thank you very much for the generous introduction and thank you, Rich, for hosting this conference. I appreciate the effort. I know how much work goes into organizing something like this. And I probably speak for many of us who are here wanting to understand if we're alone. And I thank you, because one of the things I realized coming to this conference is I'm not alone. There's many of you who are very interested and very excited in understanding how the universe works, understanding the truth. And I think that's very important. And I think that this drive and passion to understanding more about the world around us is a very important and exciting thing. It's something that really is characteristic of humanity. And I might disagree slightly with Dr. Travis in that, yes, we do deserve to know the truth. And that's something that really is important. That's something that makes humans unique. Wanting to know what's over that hill, despite the fact that it may be threatening and dangerous and scary, is one of the things that's made us great. And so I think that's a good thing. So I'm going to talk about relativistic interstellar travel. I want to be clear, I have no idea where UAPs are from, what they are, or anything like this. I'm not going to make any suppositions about this. And but I'm going to think very carefully about things that we do know. And one of the things, and I mentioned this yesterday during the panel discussions, one of the things we do know is that there is an intelligent civilization in this galaxy. There is a civilization that's interested in space travel. There is a civilization that's trying to achieve interstellar travel, and that's our civilization. So we know that it happens, and I think that's exciting and important. And if you think about this carefully, you realize that there are some implications when you start doing this. As we saw from the previous presentation, these trips are going to take a long time. And that's part of it. And so, down, there we go. The lower button advances, great. So here's a nice quote. Interstellar travel may still be in its infancy, but adulthood is fast approaching, and our dissonance will someday see childhood's end. And I'm hoping that's the case. I hope I get to see some of this. I know that NASA is aiming to get a probe to Alpha Centauri by 2069. So those who say no society would ever attempt this, no, that's nonsense. Of course, we're attempting it. We're trying to do it. We have bright minds working on this, and it's important. So we know that. We know that societies would attempt this. I'm going to consider speeds slower than the speed of light. I don't know. We have some ideas of how faster than light travel might work. We have some ideas from general relativity that you might be able to warp space-time and go faster than light, but we have seen no examples of this. We've seen craft that might be able to do something like this, but that's still supposition. We don't have data, hard data that shows that faster than light travel is possible, so I'm not going to consider faster than light travel. This is a range of speeds ranging from very slow, walking across the room, all the way up to the speed of light. There are natural objects that actually move at very high speeds. The hypervelocity star, HE, there's the number, is traveling, somewhere between about 5 times 10 to the minus 3 times the speed of light. So it's about, oops, pushing the wrong button here. And then there's a hypervelocity neutron star that's traveling even faster than this. But these speeds of natural objects are still below 1% the speed of light. So this is a figure from a paper by Garcia Escartin and Chamorro Posada. And this is a region, they call this the region of extraordinary propulsion. These are speeds faster than anything that we've ever observed. So now, we know there exists one civilization in the galaxy that's interested in this. We're interested in understanding how many there might be. The numbers that you can get in these estimates range from tens of civilizations to 10,000s. I think from Dr. Travis's talk yesterday, he had put in some numbers, and it was about 340 civilizations, something like this. So there could be a large number of civilizations interested in interstellar travel and trying to achieve it, and some may have achieved it. What you need to keep in mind is we may expect to see a wide range of technical capabilities. Some of these civilizations may have interacted with each other and might exchange technology in some way, or some may have captured technology from another society and might be able to advance in this way. But regardless of that, you still expect to see a range of technical capabilities. So I'm going to consider this. We usually you see this quantified with what's called the Kardashev Scale. That quantifies how much power a civilization can harness. It's not clear to me how useful that is, actually. I think that what's more interesting, especially if you're going to talk about interstellar travel, is how fast can you go? And we saw a scale from Dr. Travis yesterday, where he had different alpha factors, but those were related to faster than the speed of light. I'm going to consider the other end, consider things that we do know. And so here's, there we go. So here's a class, several space traveler classes. So we'll start out with class 0, unable or unwilling to reach orbital speeds. They'll come in a few different classes. There's the homeworld bound classes, so these are ones that can basically either don't leave their home world, or can orbit their home world or accompanying moons. The next classes are system bound. They're basically stuck within their star system. And then we have the near interstellar classes, which, yeah, you can get to the nearby stars, but it's going to take you 150 years to do it, right? Something like this. And then we have the civilizations that can go very fast. You're basically between 30% the speed of light and the speed of light. These are the next set of classes. And then there's the final class down here. These are the faster than light classes. I just called them class X. Who knows how many different ways there are to do this and what ranges of what you can achieve. So there's some reasons for some of these cutoffs. Here, this cutoff here within about this range here between 1% and 0.1%, the speed of light. This basically puts us into the extraordinary propulsion range. So those who are system bound basically haven't yet achieved extraordinary propulsion. The next range, so I call this class 3. 3A goes up to about 10% the speed of light. 3B gets up to about 30% the speed of light. This is important because at shielding, this is from a paper by Semyonov on radiation hazards. The shielding for somebody traveling below 30% the speed of light is relatively straightforward. You need a titanium or aluminum hull of 1 to 2 centimeters of thickness that can protect against oncoming nucleonic radiation. But you got to worry about micrometeorite bombardment, and greater than 30% the speed of light, you get rates of about 100 relativistic dust particles per square meter per second. And so this becomes very significant, faster than 30% the speed of light. So each of these is going to correspond to different engineering challenges. Once you get up into even higher speeds, you get nucleon collisions at about 70% the speed of light. That creates pion production. So you have other problems that come out here. And things get very bad once you get above 90%. Again, from Semyonov, the situation worsens dramatically for ultra-relativistic velocities. Cosmic rays basically are coming at you from the front because you get this aberration effect, and their kinetic energy is near 10 GeV. So protons coming in with this energy, the penetration depth is about 40 meters in water and 10 meters in titanium. One of the good things about this is that might not be bad for you because in some ways, because this means that protons will travel about 40 meters in water before being absorbed. They'll just go right through you, so you may not. So you get this range where they become a real big danger, and then their danger kind of drops off again because you basically become transparent to these things. So it's kind of strange. Now, of course, there's other engineering challenges, as we saw in the previous talk. I'm not going to go into those. I was more interested in some of the social implications, and because the question often comes up, what society would ever do this? And I think that's kind of a silly question, because humans will do all sorts of things that no one would think they would do. Mainly, very often just for the sake of doing them. Now, where do we sit on here? For another reason I like our scale, the scale, is because we're not class 0. We've actually done something good for us. We're no longer homeworld bound, we're system bound. We're basically sitting here in class 2A. We can traverse our star system and visit its worlds with speeds on the order of orbital velocities. So we're sitting here at class 2A, and just before I go, and with these ideas of trying to get a probe to Alpha Centauri, we're trying to jump ahead to 3A here. So we're trying to make this jump at this point, going from a class 2 traveling civilization to a class 3. So I think that's kind of exciting. I'm going to focus on these guys down here, these travelers who are able to achieve relativistic speeds, between 30% the speed of light and the speed of light. All right, so here's some travelers of potential travelers of interest. We don't know if they're travelers. We don't know where they're from. We don't know whether they're coming from another planet or not. But I'm going to look at some of these accelerations that Dr. Powell and Dr. Rielli talked about last night, and consider if these are going to be sufficient for interstellar travel. So here's real quick picture of well, there's one of these Tic Tacs cruising along, and basically they're dropping over large altitudes in 0.78 seconds. And if you go through and estimate these accelerations as we saw last night, you get accelerations on the order of thousands of G's of acceleration, which in my mind is just insane, right? It's hard to imagine. So what can you do with 1,000 G's of accelerations? We don't know whether these are interstellar spacecraft, and very often I'll have people ask me, why is it that everybody thinks UFOs are extraterrestrial spacecraft? And the answer is pretty simple. It's because the observed accelerations are consistent with that hypothesis. You can ask that question, and the answer is yes. So here's actually, I estimated the accelerations of several other situations. This is a sighting by Graham Bethune in 1951. He basically had a craft cover 15 miles in less than a second, and you're looking at about 2,000 G's of acceleration. The Japanese airliner that was followed by a UFO for about 45 minutes. This UFO, every time the height-finding radar would sweep every 10 seconds, this craft would jump from 1 o'clock to 6 o'clock, around the craft, staying some distance away. I think it was about 7 miles, if I remember right. If you assume that the craft accelerated straight over the airplane into the next location in 10 seconds, then you get accelerations around 300 G. If you assume that it's moving in circular motion around the aircraft, then you're getting accelerations of 1,800 G. So still these things are accelerating very, very rapidly. So with several of these cases, you can see we're getting accelerations on the order of 300 to 2,000 G. These really are what we would consider, some people might say, are impossible accelerations. So to work with this, we find if you can, I'm going to assume that these accelerations can be sustained. So yes, these accelerations have been observed. That's interesting. We don't know how long these craft can sustain these accelerations. And so that's one of the capabilities that as far as I know, we don't have any data on. I'm going to assume that they can sustain these accelerations for long periods of time. So there's an assumption here. What you find is very rapidly these craft get up to relativistic speeds. And we'll see how rapidly this happens. So to do some of these calculations, you need to use these relativistic rocket equations. These are the equations here. I'm not going to go into detail here, but there's a few different times you need to keep track of. Well, first, A is going to be the acceleration of the spacecraft. There's 2 reference frames you need to keep track of. There's those of us who are sitting around and hanging out in the galaxy. So we'll call that the galactic frame. And then there's the time tau, which is going to represent the time that elapses in the spacecraft. That's the proper time that they experience. Those 2 times are going to turn out to be different. And that's significant. It turns out that traveling at relativistic speeds works with you if you're trying to achieve interstellar travel. It's good news for us. So here I'm going to consider, here's several of these cases. How far can you get over some period of time? I'm going to assume that they accelerate halfway and then decelerate the other half. So what can happen? Well, how long will it take to get to Alpha Centauri? So for, here's one case where I estimated about 100 G for the Nimitz case. If you accelerate at 100 G halfway and then decelerate another 100 G, you can get to Alpha Centauri in about 45 days. Now 45 days is the time experienced by the spacecraft, not the time that we experience. And it's important to keep make that distinction. For those here on Earth, it'll take close to 5 years to get to Alpha Centauri at those rates of acceleration. I'm going to mainly focus on 100 G. It's a nice round number, and it's a lower end of what's been observed, right? And so some of these Tic Tacs have been, or these craft have been seen moving at thousands of G. Yeah, you could do a lot better. if you, like the case with Bethune, if you can accelerate at 2,000 g and sustain that, you can get to Alpha Centauri in about 3 days ship time. That's fantastic. I would say, so to anybody who says to me, why do you guys think that some of these craft might be interstellar spacecraft? I would say because these accelerations are consistent with interstellar travel. Not only would that tic-tac not only is it reasonable to assume that it's an interstellar spacecraft, it's reasonable to assume that it's an excellent interstellar spacecraft. It's something far better than we were hoping to do, right? So I think that's exciting. 40 light years out, just accelerating 100 g, you can get there in about 2 months. That's faster than it takes us to get to Mars now. You can get out to Zeta Reticuli. But if you go further, again, assuming that you can sustain these accelerations, that's a big assumption. We don't know if that's possible. You can get out to a distance of about 1,000 light years in less than 3 months of time if you're accelerating at about 100 g of acceleration. How long would that take us for everybody studying the galaxy? It would take you over 1,000 years. We'd be watching your spaceship over 1,000 years, traveling, 1,000 light years. It would take a long time. Why would anyone do that? Because for the people on the spaceship, it takes less than 3 months. That's why you would do it. The bad thing is that when you want to come home, you're not going to make it home in time for dinner. And I put it that way because that's why we see faster than light travel in science fiction stories. In science fiction stories, you want Luke Skywalker and Han Solo to take off in the Millennium Falcon, go fight a battle on a distant star system, and then come back home for dinner, right? That's what you want to have happen. So how do you do that? Well, you have to have faster than light travel. Well, if you don't have faster than light travel, you have to accept the fact that you're not going to be home for dinner. You're not going to be home. You're not going to come back to the same country. It's going to be far different. And it depends on how far you travel. You can get to the other side of the galaxy, accelerating at 100 g, in less than 4 months. That's ship time. So you can travel. I could hop in as one of these spacecraft, accelerate at 100 g, halfway, decelerate at 100 g, halfway, get to the other side of the galaxy in 4 months, faster than it takes us to get to Mars, and come back. Now when I come back, it's going to be about 150,000 years later, right? So, so why would anyone do this? That's crazy, right? Well, the civilization wouldn't do it. They wouldn't, so like Dr. Conley described, no civilization would send probes out to collect data because it's going to take 150,000 years for the data to come back. That's difficult. That's not going to really work. But if you're an adventurer and you want to go on a cool trip, you could do that. You're just not going to come home. You have to give up on that idea. So here's a cartoon of the galaxy, and here's our sun located in the galaxy. This is basically the range of your ship traveling at 100 g of acceleration. You can get that far in about 110 days ship time. Now the engineering challenges are formidable. You're traveling at over 90% the speed of light through a good leg part of this trip, through some pretty dense areas. What's working for you is that relative to people in the galaxy, they see your clocks moving more slowly due to relativity. Time is slowing down in the spacecraft, and so so we look at the ship. Well, of course it'll only take them 4 months their time to get to the other side of the galaxy because their clocks are moving slowly. Now, from the spaceship's perspective, time is moving normally. What's changed there is the distances have shortened. So the distance you have to travel to get from one side of the galaxy is dramatically shortened. So you don't have to travel as far. That's basically their perspective using relativity. that has really serious consequences because space isn't empty. You have about 1 hydrogen atom per cubic meter, and now you can track all that distance, getting up to relativistic speeds, and I'm now no longer flying through kind of empty space. I'm traveling through a hydrogen cloud at close to 90% the speed of light, and this is going to very quickly tear your ship apart. So you have to really worry about shielding. The engineering challenges are quite terrifying. So whether anyone could really accomplish this is still anyone's guess. It's not a physics problem. It's not a physical impossibility. It's an engineering challenge. And engineering is all about being clever and working around problems, and that makes engineering advances very unpredictable. So what kind of speeds do you get up to? So here we go. I have 1g acceleration, a nice comfortable 1g acceleration. After 200 days in the galactic frame, you're already getting close to half the speed of light. So very quickly you go and get into class 3, near interstellar travel, and out here you're basically into the relativistic regime. So after 100 days of accelerating at 1g, you're traveling at very high relativistic speeds. Of course, with faster accelerations, 10g, this happens much faster. And I was considering 100 g's in the example before. Here you basically are getting up into the fast relativistic regime within 1 day. So if we look at these tic-tacs, well, here's the 1000 g. These tic-tacs, if they can maintain acceleration for about 1/10 of a day, maybe 2 hours or so, basically they're already into the relativistic speeds. So that's an interesting question that I have. Yes, these tic-tacs exhibit high accelerations. How long can they maintain them? If they can maintain these accelerations up to a few hours, then they can become very relativistic. And that's interesting. If they can't, if they can only do this for short periods of time, it's going to take a lot of work to get up to these speeds. So here's a little post from a little blog from Dr. Kaku. He says, when discussing the possibility of interstellar travel, there's something called the Giggle Factor. Sometimes scientists tend to scoff at the idea of interstellar travel because of the enormous distances that separate the stars. Basically, it's going to take you a long time to do it. Well, the one thing I've shown you, yes, it will take a long time for those of us sitting around on our home worlds, but it's not going to take a long time for the travelers. So what would happen if we did start traveling at these very high relativistic speeds and went on these adventures? How could you do this? Well, so let's say that me and Matthew here and Rich all go taking off in different directions, and we're going to go explore the galaxy. So we're each going to go to a different corner of the galaxy, see what's there, and we're going to come back here and meet back here on Earth. If we plan the trip right, we can pull this off. We could actually meet back up. We travel the right distances at the right speeds. We'll come back here and we can meet back here in, say, 8 months our time. Come back here next year, perhaps. And if we do this properly, then yes, we'll come back here. It'll be 150,000 years later, but we won't see any of you, but we'll be able to meet up. So there is a society that would do this. And this is basically what I'm explaining here. So there is basically what's happening is space and time are interlinked. Traveling at very high speeds through space is the same as traveling through time. You're traveling into the future, basically. So this is an interesting website. You don't have to be a space explorer. You can be a time explorer. Let's go see what Earth looks like in 150,000 years. You could look at it that way too. And that would be another way to have an adventure. The way to pull this off, any society that's basically traveling like this is going to have to be nomadic, because you aren't going to have a homeworld to come home to. The next time, if I took off to one side of the galaxy and came back again 150,000 years from now, I'm pretty sure there isn't going to be, the countries that exist today aren't going to exist in 150,000 years. I'm willing to bet on that. I'm not even sure people will be here 150,000 years from now. So that's a difficult trip to make. If I'm going to make that trip, I'm going to want to make it with lots of friends, so that when we do come back, I have some people to trade with, to help each other, and we can help out. So you can become nomadic. And so this is one of the ideas I've had, that anyone traveling at relativistic interstellar, performing interstellar travel at relativistic speeds is probably nomadic. That sounds kind of strange. A lot of us, since our society is not nomadic, we would think, who would do this? Well, there are nomadic societies on Earth. Here's one example. The Bashar Laut are South Asian people, and they live in the seas around Malaysia, Indonesia, and the Philippines. They live on their ships. They live on their boats. That's where they live. And this is what aliens who are traveling interstellar, performing relativistic interstellar travel would have to do. It's doable. People do it. There are societies that do this, so it's not too far out to imagine that there may be other societies who would do this. There's some difficulties with this, which I found interesting. The meetup times are not easily prearranged, especially if you have a relatively large society. If there's 3 of us, we can easily make a plan, head off, and then meet up again. But then if we come back and Rich and I get here and Matthew doesn't show up, now we have a bit of a problem. So what are we going to do about that? How do you arrange things to make sure that happens? Let's say this whole conference, we all learn how to perform interstellar travel, and we all decide to go take off on an adventure, and we'll meet back here a year from now. That's fine if you're going to arrange meetup points for the next meetup point is here, the next meetup point is here. But if somebody happens to miss a meetup point, how are they going to meet up with everybody else? You're slowly going to lose people in your society. So you have to come up with a plan for traveling that minimizes misses, right? So that you don't lose members of your society. A breakdown would be horrible. You know, you're flying along and your ship breaks down. What are you going to do? Call for help? It's going to take 150,000 years for somebody to come from the other side of the galaxy to get to you to help you. That's not feasible. So what I've started doing is I've started modeling interstellar networks of relativistic travelers. And I'm going to give you some idea of how I've been doing this. So here's our cartoon of the galaxy. I'm going to consider stars mainly within this region. This region is called the Galactic Habitable Zone. Near the galactic center, well, the biggest problem is the stellar densities are very high. There's a lot of stars. The chance of flying into something is really huge, and there's a lot more debris. So you really probably don't want to fly through this region at relativistic speeds. It's already a bad idea to be flying around at relativistic speeds anyway. It's a worse idea to be flying around here at relativistic speeds. But then the question is, where would you like to go? Well, it turns out that the metallicities of the stars, which basically is the proportion of heavier elements in the stars, are higher in the center of the galaxy. And from what we know at this point, this typically results in an excess of gas planets, giant gas planets, and a deficit of small rocky worlds. So for those of us who live on rocky worlds, you probably aren't going to find many interesting places here. There are probably some places, but the probability is lower. The same thing goes out here. The metallicities out here are lower, and so you probably have fewer rocky worlds out here. So there probably isn't much to explore out here either. You're probably going to stay mainly within this zone. Now I made this probabilistic, so so I put on a density plot. The density falls off very quickly in the middle, that's basically to exclude this region, but it falls off more gently out here because there still could be interesting stuff out there. And I use this cartoon, which isn't horrible, to basically model the density of stars. And so when you combine this with the habitable zone plot, if you take the product of these two, you basically get like this, something like this. So this is basically a picture of the places, the white areas are places where you probably find stars that would be interesting, star systems that are interesting. And so then I did some Monte Carlo sampling of star systems. I sampled about almost 2 million star systems in the galaxy. And if I select 1,000 of those, they basically are around here. So you can see that more stars are located in the spiral arms than not. So I basically use this to pick viable or potentially interesting star systems. So this is actually one of the networks I modeled. It's basically a tree structure network, and so it's driven by system discovery. So they start out at a home world. I'll go with this diagram. A home world here, and they discover a few star systems nearby that look interesting. They travel and check them out, and from some of these star systems they discover other ones, and so on. And the system, the network kind of grows this way. The bad thing is that I don't have travel routes connecting nearby stars that are far away from the homeworld. So this is a tree structure network. You might want to consider other types of networks. So the network topologies are going to make a difference in how well this actually works. So I'm going to show a video here of some interstellar travelers. On this network. So here are the first star systems. There's their homeworld. They're traveling to these star systems. These red dots are basically caravans. And this is the year in the galactic time. So this is after 100 years galactic time. Some of them have made it to the first star system, are coming back, and others are still continuing on their trips. At this point, more are discovered. So here you can see somebody made it to this star system, is heading back, but then another subset of the travelers traveled to these star systems from that one. And we're up to 200 years now. And when we're all done, I'll show you how much time has elapsed for each of the travelers. We'll see how well this works. Now, one thing you'll notice as this progresses is that there's not a lot of meeting up going on. And here you can ask the question that Enrico Fermi asked, where is everybody? They're all traveling. Why? Because it takes thousands of years to get anywhere, or hundreds of years to get anywhere. Everybody's en route. That's where everybody is. Why are they not here? They're traveling. It takes a long time in our reference frame. In their reference frame, it takes a few months. So the perspectives are very different. So this will keep progressing. I actually have this run until about 2030 years. So the network keeps growing, and you can see what all the travelers do for 2,000 years. I'm going to advance the slide, and we'll talk more about this. This just continues. They just keep going around. You don't have a lot of meeting up going on, and that's partly because it's a tree structure network. It would be much more advantageous to put in routes that are connecting some of the, it's not advancing.
Oh, it's not?
That's all right.
Try now.
Thank you. Yeah, so these 50 travelers in the simulation do not often meet up. So there's some work to be done to come up with network topologies that are going to better maximize meetups. So there's some interesting research here, because an interstellar society isn't going to just take off and then let's see if we can meet up, because it's just not going to work. There's some work to do to figure out what type of planning would have to be done beforehand to make it more probable so that people meet up more regularly. So you can do this in part by choosing path lengths that are integral factors of a relatively small number, maybe less than 1,000 light years. So, for example, let's say we choose 40 light years. We're going to stay close to home. We're going to travel 40 light years. So you choose paths that are either 40 light years, maybe 20 light years, or 10 light years. So if I choose a 40 light year path, and Rich, you choose a 20 light year path, you're going to have to make 2 trips to meet up with me after my one trip, and then you can do it. So the other thing is you can adjust your distances a little bit you can adjust your path length to make sure that these are integral numbers of some pre-chosen factor. So you can do some adjusting. Traveling on arcs is one way to do that, and that's beneficial for a few reasons. It keeps you out of the galactic plane where there's more dust and stuff to fly into. If you travel on an arc, you can actually stay out of some of the debris. And then you can better control your path length, which would be useful. So some candidate distances, so I kind of played around with this. Some candidate distances for that would be useful would be either 600 light years or 840 light years. 600 is good because it has 24 factors, and 840 has 32 factors. These factors look like this. 600 is good because 60 is divisible by a whole bunch of numbers. So this is one reason why this is a good number. This is actually why the Babylonians used the space 60 system. I want to be a little careful here. The idea of invoking the Babylonians here has to do with the base 60 number system and nothing to do with ancient aliens or anything. They're totally distinct, nothing to do with each other. So I don't want to be any. I realized that after I made these slides, I thought people might think that, there's a connection. No, there's no connection. The connection is that 60 is a good number. That's the connection. And they were clever. 840 is even better because then you have 32 factors to play with. This is good because if you are working with 840, then if you stay close to home, there's plenty of distances here that are integral multiples, where multiplied by an integer will give you 840 between like 50 light years and 60 light years. But it's the factors are pretty dense between 20 light years and 300 light years. So I would probably play with 840. I plan to do a lot of simulations to see what works best. And you're probably going to want to, there's a lot of other things to worry about. You're probably going to want to have closed loops. It increases the number of paths you can take, which gives you more commensurate distances. The real problem, another real problem is this one. The star positions are not constant. The stars move. They basically move on the order of the time scales that are involved in traveling. So you take off to one side of the galaxy and then come back again to where you thought Earth was. Well, it's hard to pick a reference frame. This is another part of the issue. The sun will have moved around the galaxy by about 100 light years. It's not a trivial distance. So this is something, navigation is going to be a very serious issue. For lots of reasons. First, you get 30 light years out and you can't see the sun with the naked eye anymore. So, which star is ours again? Oh crap. There's a lot of stars. You don't want to get lost out there, especially because it can take a long time to get anywhere. You don't want that to happen. And then on top of it, the stars move. So you go away and come back again. Where'd it go? So one of the things that I think is interesting is if we ever are able to get our hands on an interstellar craft from another civilization, I want to figure out how their computer works. Because on board, they have to have a navigation computer with information about most of the galaxy. Because they have to know all the star positions and their relative velocities. and they have to, run this while they're flying to be able to get anywhere. Otherwise, it won't work. So onto these spacecraft have to be incredible databases of amazing amounts of information. That to me is really, really exciting. The big problem is you probably wouldn't recognize one of their computers if you saw it. That's really the issue. There's other things to maximize. You probably want to maximize the rate of information transfer as well as supply transport. You need to transport supplies across the network when you meet up. You want to exchange information about what you discover. So the designs of these networks and their topologies would probably be have multiple optimization criteria. The first being you need to be able to meet up with your buddies, and then the later ones is you want to be able to maximize information transfer and supply transport. So simulations of complex life in the galaxy, there's a paper by Unama et al., 2007. They basically simulated the emergence of life on planets. Of course, this is based on a lot of postulates and based on what we know so far. What they found in their simulations I thought was interesting. Earth-like planets with primitive life are approximately 30 light years distance from one another, and Earth-like planets with complex life are approximately 130 to 200 light years distance from one another. So these are going to play, whatever these real numbers are, these are simulations. Whatever the truth is going to place huge constraints on a network of interstellar travelers. So if this is correct, then it's reasonable to expect that there's probably local subnetworks of interstellar travel routes between worlds ranging from about 30 light years to out to around 100, 200 light years and beyond some range beyond that. And this is another reason why 840 light years would work for choosing path lengths, because you have plenty of factors of 840 that lie between 30 light years and 200 light years. So you might be tempted to consider larger numbers because you get more factors, but because there's more factors, you're going to have to make many more trips back and forth before you meet up with your buddy who made one trip. So that eventually won't. So there'll be some optimal point, and then there'll be a fall off. There's an interesting math problem here. Where's that optimal point and where's the fall off? There's some interesting work to be done there too. So if you're going to model interstellar networks, there's a number of interesting model parameters. You first, of course, choose a system of origin, which is perhaps the original homeworld or homeworld after colonization or something. How many travelers are there in a network? How many star systems in the network? What's the volume of space encompassed? Number of travel routes? These things. So, and then some of these will govern network formation. What is the average discovery distance? Basically, at what distance can travelers detect an interesting planet? What constitutes an interesting planet? This branching ratio, how many interesting planets are typically found from a given location? And then what is the distribution of heavily trafficked routes and less trafficked routes? I'm interested in this because I do a lot of work with Bayesian data analysis, which is basically model-based reasoning. And so I find this exciting because if we do encounter interstellar travelers and we want to learn about them, without just talking to them, which would be the easiest way to learn about them, of course. But if we do want to learn about them and make inferences about what they're like based on their behavior, one of the ways to do this is to have models of what these interstellar networks would look like, and then you can basically make inferences where you're able to calculate probabilities for these model parameters based on the data that you have. So basically one way to do this is what data might we have, and some of this data might be very sparse. You might only have one data point, which is basically they found Earth, right? So you might know that they found Earth, and you might want to know how far away did they come from, where did they originate from, how big is their network, and things like this. You could still estimate probabilities of these things based on these types of networks, and so I think that's interesting. So these models will make testable predictions, which can be useful here. And with any inference problem, you won't get definitive answers, but you can obtain probabilities for potential answers. And the other thing I thought was interesting once really thinking about this carefully is I realized such travelers would have a very different perspective than we would. So if you're basically traveling around so that it takes 4 months in your ship time, but in the galactic frame it takes 80,000 years or 100,000 years, you can imagine, let's say we fly up from the sun to the other side of the galaxy, and then back again. A round trip is basically going to take, or each way is about 80,000 years, so a round trip is about 160,000 years. So two round trips across the galaxy would take about 16 months travel time, but it would take 300,000 years in the galaxy's time. So basically you're traveling into the future. I didn't mention what the travelers experienced in my little simulation. I ran that for about 2,000 years. The travelers basically, let me go back, sorry about that, oops, wrong way. Yeah, the travelers basically experienced a range of elapsed proper times from about 7 months to 2 years. There's some dispersion based on how far they travel, but over a 2,000-year period of galactic time, the travelers experienced anywhere from 7 months of travel time to 2 years. So it's a big difference. So this perspective was interesting because I could go out traveling for 16 months and come back and it would be 300,000 years later, which is insane, right? But that's physically possible. What this means is in a 50-year lifespan, in my whole lifespan, if I traveled my whole life, I could conceivably traverse the galaxy 150 times, which is equivalent to racing ahead 12 million years into the future. So I've heard people talk about UFOs and say they've been coming here a long time. It could be far longer than you think. And not only that, the ones who came here 12 million years ago could be the same individuals that you see today. So there were sightings of flying shields, or orbis clypeus, in ancient Rome, reported in ancient Rome. Some of those craft could be the same craft that were seen in Ohio last week. They could be the same individuals. And I don't think this is anything that anyone's thought about. I've never heard anything like this in science fiction or anything. But this is really how it could work. Yeah? Which is really mind-blowing. So then you ask questions. And you mentioned this, our civilizations become ephemeral. And people always ask questions, why don't they land on the White House lawn? Well, first, why the White House and not anywhere else on the planet? But why don't they make friends with the locals is really the question. Because we're ephemeral. The next time they come back here, we're gone. There's no one to make friends with. For them, the whole universe is pretty much ephemeral, right? They're living 12 million years. For us, for them, we're a flash in the pan. It would be like you making friends with a dandelion in your driveway when you go off in the morning to work and you come home and it's wilted. What's the point? Right. You might make friends out of curiosity. You certainly could study them. I mean, we do that. People study fruit flies. You don't make friends with them. How long do fruit flies last? It's hours, right? This is really an interesting explanation as to why they don't make friends. There's no point if you're like this. Being able to race 12 million years into the future is really great. You could watch evolution at work. The last time one of these guys could be here, this is what America could have looked like, right? And they come back 50 years later, let's go visit Earth again. I haven't been there for 50 years, let's go back and, holy cow, what happened? This is cool, right? Well, there's a lot of opportunities. You can watch evolution happen. That would be cool and fun, right? You could experiment with it. You can experiment with evolution. And not just your society. Individuals could experiment with evolution, which is more likely. And I think that's interesting. That would be a real possibility if you did this, which I think is kind of cool. So here's a paper by Stothers on unidentified flying objects in classical antiquity. It says these fall neatly into the same categories as modern UFO reports, suggesting that the UFO phenomenon, whatever it may be due to, has not changed much over 2 millennia. And you think, wow, that's amazing. Why haven't they advanced? Well, because they're the same individuals. I'm driving the same Honda Accord that I had 15 years ago. And that was 2 millennia. Remember, I ran that simulation. How long was 2 millennia in their frame? 2 years. Right, so 2 years for 2 millennia. I've got my Honda Accord for 15 years. So somebody's gonna look at my Honda Accord if I flew that in every now and again. They're gonna say, they haven't changed their craft in 14 millennia. 14,000 years, they're still flying the same craft. Well, yeah, I'm trying to save money. I don't want to buy a new ship. It still works. The perspectives of these travelers would be so different. It's not just a cultural difference. It's a very different difference that I don't think has really been considered. Another important point is there's no point in radio or laser communication. Why? Because the transmission speeds, the speed of light, are on the order of the craft speed. Why communicate with your buddy? You're just going to meet up with him anyway in about the same period of time. So there's really, I like to think of it this way. Time dilation makes sneakernet more efficient. And so sneakernet is when you walk your software over to your friend rather than transfer over the internet or wireless, right? The bad side is stranded craft are going to have to wait for hundreds to thousands of years for help to arrive, which is not going to work. But this puts constraints on a traveler density. So if you're going to have a network of interstellar travelers, it's going to have to be pretty well populated so that if there are accidents or problems, you have a chance of being helped. But I really don't think they'd be communicating with each other. I don't see why there'd be any point to doing it. So sorry, SETI. And that's basically it. Thank you.